Yesterday we multiplied radical expressions. So that means today we are dividing radical expressions. So our job is, how do we divide? Just like multiplying, as long as they are the same type of root, we can divide them. It's just going to be a matter of knowing how to simplify them. So that blue paper, your calculator are still going to be wonderful, helpful things. As we look at example A here, my suggestion of your first question that you should be asking yourself inside your head, before you even think, can I take the square root? This is a square root and a square root. Can I divide them? So 18x to the fifth divides by 2x to the third. That should be your first step. If they divide, they won't always divide. You'll notice that at the bottom, they won't always divide and simplify and be nice and neat for you. But if they divide, you should start by dividing them. And so you can even think of this, if you want, as one big square root, where it's the square root of the fraction of 18x to the fifth over 2x to the third. So when you have a square root divided by a square root, you can make it one big square root. Kind of like what we did with multiplying. Now, you guys said it divides. So what is this when it simplifies? What is 18 divided by 2? 9. Oh, that's nice. What is x to the fifth divided by x to the third? X to the second, because when you are dividing and the bases are the same, you subtract the exponents. So 5 minus 3 is going to be x to the second. That just got a lot nicer, didn't it? Because now we went from having a fraction to work with to just having, okay, this is like yesterday now. Can I simplify? So can I do the square root of 9? Yes, the square root of 9 is 3. Can I do the square root of x squared? X, because how do we do square root of an exponent?
Divide the power by the power.
Yeah. Since this is a square root, there's that invisible 2 there. And so in order to do that, I'm going to divide the power by 2. And 2 divided by 2 is going to make this x to the first, which I can just write x. And at that, we're done. Now, something I need to comment, because I think I forgot to comment yesterday. I didn't think to look at this morning in the homework, but did anyone start homework last night? Was it requiring absolute value?
No.
Okay, so here's what I'm going to say. Lesson 6.1, we had to use absolute value when necessary if we needed it to force a variable to stay positive. Once you get past lesson 6.1, you usually will see a statement in the directions that says assume all variables are positive. If you see that statement that says assume all variables are positive, well, if you know the variable is positive, do I need absolute value to make it positive? No, because the directions are saying assume the variable is positive. So I believe the rest of this chapter, we won't use absolute value because we would spend a lot of time doing absolute value. Now, if I go off the top of my head, and this is the assignment I used last year, I think there is one tricky one in there that you have to have absolute value on somewhere. So just beware. I think it does pop up at least once in homework tonight, but for the most part, you're not seeing it. Am I making sense here? Okay. Yes.
On one of them, it was like the distributive property method. So it wasn't like something that we hadn't learned yet because it wasn't division. And I didn't really know how to do that.
Yeah, it was like the square root of 1 and then in parentheses something, like the square root plus.
I know which one you're talking about, and I really shouldn't even have that one in there till next lesson. And
Yeah, I didn't know.
okay. We'll talk about that one later, though. I know which one you're talking about. Remind me at the end of class if we have time, or tomorrow at the beginning of class, okay? Okay, ready to talk B?
Sure.
So first of all, are these radicals divisible?
Yes.
Well, first of all, let's identify, are they the same type of radical? Yes, they are both cube roots, correct? So we can go ahead and make this a one big cube root. So it's going to be the cube root of 162 y to the 5th over 3y squared. So both cube roots, I can put them together. Do they actually divide? Yes, you're seeing some pieces that divide. Does 162 divide by 3?
Yep.
Yes. And so I'm going to have, still going to be a cube root. So we're still under that radical. 162 divided by 3 is 54. Does y to the 5th, or not does it, what is y to the 5th divided by y to the 2nd? Okay, 5 minus 2 is 3, so y to the 3rd. With all questions, I like to ask, are you done? And what do we need to check for to decide if we're done? In this case, it's not are there any perfect squares, it's are there any perfect cubes. And so, I don't have mine beside me. Blue paper, right? 54. So I'm going to go to my middle column on my blue paper. Is 54 in that middle column?
No.
No. So there's two numbers that are smaller than 54. Does 54 divide by 27?
Yes.
Oh, it does. 54 divided by 27 is 2. So is there a perfect cube in 54? There is. So now we're back into that simplifying step we took yesterday. So I'm going to take this cube root, and you remember how I broke it into perfects and leftovers, basically? So you just said 54 divides by the perfect cube, 27, and the leftover piece is 2. So 54 is still there. It's 27 times 2. Y to the 3rd. Am I going to be able to take the cube root of y to the 3rd? Yeah. Can I take the exponent of 3 and divide it by the root of 3?
Yeah.
Yeah, so I'm just going to leave it as y to the 3rd, because I'm going to be able to do that. Okay, do you know how to finish it up? What is the cube root of 27? 3. So that's going to go outside my radical. What is the cube root of 2? Okay, it's cube root of 2. It's some decimal, right? I mean, your calculator can tell you some decimal. So that 2 is going to stay inside the cube root. What is the cube root of y to the 3rd? Why? Because what are we going to do? We're going to divide that by 3, aren't we? Okay, we're dividing it by this guy over here. And 3 divided by 3 is y to the 1st. Where am I putting that y to the 1st? Because I was able to simplify it outside. You can write y to the 1st if you want. I tend not to. So 3y cube root of 2. Some of what we did yesterday coming back to you in the midst of this? Because that's it. You can't forget what we did yesterday. Okay, C. Square root of 50x to the 6th divided by square root of 2x to the 4th. Can these become one radical?
Yeah.
Yeah, they are both square roots. So square root of 50x to the 6th over 2x to the 4th. Can they divide?
Yeah.
Of course they can, because they're in the top section of notes here. Okay? So, I'm going to keep my square root. What is 50 divided by 2? 25. What is x to the 6th divided by x to the 4th? 6 minus 4 is 2, so x to the 2nd. Can I go farther? Yeah. Do I know the square root of 25? It's 5, so that's going to be outside my radical. Can I do the square root of x to the 2nd?
Yeah.
Yeah, because this is a square root. 2 divided by 2 makes it x to the 1st. So 5x. And again, no absolute value. It doesn't say it here, but most of your homework is going to say assume all variables are positive. Okay, you're catching on here. Now, of course, we had to start off with the ones that they're going to work out, right? They worked out in that I didn't really have to worry about them being a fraction too much because they divided so nicely. It just, it made life nice on us. If you glance at the bottom, which I will say, I know some of you are going to jump ahead of me, it's this first one here that I'm going to change, and we're not going to do a cube root there. We're going to do a square root. But as you start looking at those, does 5 divide by 12?
No.
I got x on top. Does anything divide? No. Can I just leave it under the radical? No. So this is where we're going to talk about something called rationalizing the denominator. And you've seen rationalize the denominator before. That would have happened back in Algebra 1, I'm pretty sure. But the idea is when you work with radicals, so square roots, cube roots, all those little root signs, there's a basic principle that roots are not to be left in denominators. So the idea that you can't have a square root or a cube root or whatever in the denominator. Along that same line, that does not mean I can just make it one fraction under the radical, because I still technically have a root in the denominator. And so we're going to talk about how you can rationalize. Notice it says to eliminate roots in the denominator, we use the process of rationalizing the denominator. And I'm going to do a basic example right here in this area. One over square root of 2. Okay, and this is an example to demonstrate how to rationalize. And I'll do a square root example, and I'll also do a cube root example. Square root of 2 is not okay. And can I take the square root of 2? No. Now, what we want to do is we want to multiply square root of 2 by something that will make it a number I can take the square root of. And the easiest thing to do is to multiply it by its self, which in this case is 2. So typical rationalization technique is you multiply the radical by itself. So by multiplying square root of 2 by square root of 2, we're going to make it a perfect square. Now, you guys are well trained and you know whatever I do to the denominator, I do to the numerator. So whatever I do to the bottom, I do to the top. So that means I'm also going to multiply my numerator by square root of 2. Okay, let's do a little cleanup here. On top, what is 1 times the square root of 2? Square root of 2, when you multiply by 1, just stays whatever the other item is, right? So square root of 2 times 1 is just square root of 2. What's square root of 2 times square root of 2? In the end, I'm going to say 2. If you want that middle step, some of you do, some of you don't. Square root of 2 times square root of 2 is square root of 4. But what do you know about the square root of 4? It's 2. So that means my denominator can become 2. My numerator stays square root of 2. The step I will try, or the connection I'll try and get you to make, is that when you multiply a square root by itself, you're always going to get whatever's under the radical. So square root of 2 times square root of 2, the shortcut, it's 2. The long way, square root of 2 times square root of 2 is square root of 4, which is 2. Okay? So that's an example of rationalizing a square root. Let's do the same thing but with a cube root. Because a cube root you have to think differently. So basically I'm going to take the same problem I just talked about, except we're going to change it to a cube. Now, can I take the cube root of 2? Of course not. That's the whole point, right? And I can't leave a radical in the denominator. So the question becomes, what can I multiply cube root of 2 by that will make it into a perfect cube? Now, we can use the paper to help us on this one before I explain it. But if I multiply 2 by 4, I'm going to get 8. And 8 is a perfect cube. Does that make sense, what I just said there? This is a 2. The first perfect cube on my list is 8. 2 times what is 8? It's 2 times 4. Now, officially what we're doing, okay, it takes 2 of something to make a perfect square, right?
Yeah.
How many of something does it take to make a perfect cube? 3 of something. And so the idea here that I can say is that I can multiply by, it's the cube root. If there's 1 2 here, how many more 2's do I need to make a perfect cube?
2.
I need 2 more 2's. And so we can think of it as 2 squared. But what is 2 squared?
4.
That's the 4 you guys just said, isn't it? So as I said, this one's a little bit more difficult to think. But the idea is it takes 3 of something to make a perfect cube. So if I already have 1, we're going to multiply by 2 more, which is the 2 squared. So I'm going to multiply the cube root of 2 squared, top and bottom. On top, what is 1 times the cube root of 2 squared? Cube root of 2 squared, or I'm actually going to say at this point cube root of 4, because that's what I would express in my answer. Denominator. Cube root of 2 times cube root of 2 squared. Cube root of 8. But what do you know about the cube root of 8? It's 2. So cube root of 4 over 2. The idea, if you have 3 of the same thing under a cube, it's going to be a perfect cube. Something I probably need to address, I just realized. On both of these answers I just did, I stopped here because this is a final answer. Why am I not reducing 2 over 2 and 4 over 2?
Because they don't have the same thing.
Yeah. This is a square root of 2. In order to simplify a square root of 2, I need another square root of 2. This is a cube root of 4. I would have to have a cube root If I wanted to reduce these, it'd have to be like a cube root of 2. They both have to be cubes. Does that make sense? If they're both cubes or both squares, then yes. But since one's inside a radical and one's not, they are separate. Okay. Let's attempt this bottom one. Now, I changed it to a square root. Everyone saw that, right? Square root of 5x squared over 12y squared z. Does anything divide? Nope, nothing divides. So, I would start off by asking yourself, are there any perfect squares I'm going to be able to take? And that's what I would start off thinking here. Five. Are there any perfect squares in 5?
No.
I mean, the only thing smaller than 5 on my list is 4. And does 5 divide by 4? No. 5 is a prime number. It's going to be fine. And are there any perfect squares in x squared?
Yeah.
In all actuality, x squared is a perfect square. So here in my next step, I will take the square root of x squared. What about 12?
3 and 4.
Oh, does 12 have a perfect square in it? Blue paper, right? What's 12 divide by here? It doesn't divide by 9, but it divides by 4. So I'm going to take the 12, instead of writing 12, I'm going to write 4, and 4 times what is 12? 3. So 4 times 3. So I split that up into perfect square and leftover piece. Y squared? Well, here in my next step, I'm going to be able to take a square root. Z, are there any perfect squares in Z? No. But this is where, you know, if you had, say, Z to the 3rd or Z to the 5th, we'd be splitting it into perfect square and leftover. Okay, let's clean up what we have right now. Trying to decide how I want to write this out. I think for the benefit of what we're doing, I am going to make it 2 fractions. Okay, on top. Can I take the square root of 5? No, it's going to stay 5. It's going to stay under the radical. Can I take the square root of x to the 2nd? Yes, because how do I take the square root of an exponent? We divide it by, in this case, the 2. 2 divided by 2 makes us x to the 1st, and that's going to be outside the radical. Are we okay with that? Okay. Denominator. Can I take the square root of 4? Square root of 4 is 2, so I'm putting that in my denominator, but out front. Can I take the square root of 3?
No.
No, so 3 is going to stay inside the radical. Can I take the square root of y to the 2nd?
Yes.
Because I can take 2 and divide it by 2, which is going to make it y to the 1st. And that's outside the radical. Can I take the square root of z? Z to the 1st. That doesn't divide by 2, so z is going to stay under the radical. Okay. There wasn't anything we could divide. There were some perfect squares I pulled out. Can this be a final answer?
No, so those thingies in the bottom.
Define thingies in the bottom.
The square root.
Okay, there's a radical in the bottom, yes? And this is where, because right here, this radical in the denominator, I can't stop here. I have to go a little farther because I have a radical in the bottom. Now, if I have the square root of 3z, how do I make the square root of 3z a perfect square that I can take the square root of? So how did I make the square root of 2 a perfect square? I times it by 2. I times it by its self. How can I make the square root of 3z a perfect square? Times it by itself. So I'm going to multiply my denominator by square root of 3z. What I do to my denominator? We do to my numerator. So I'm going to multiply my numerator by square root of 3z. This is called rationalizing the denominator. That's what I'm doing right now. So I can't leave that radical in the denominator. Okay, final bit is any cleanup we can do. So, where are we at here? On top, I have an x outside that's going to carry down as x outside. What is the square root of 5 times the square root of 3z? Square root times square root, you just shove them together and multiply. So square root of 5 times square root of 3z is square root of 15z. On the bottom, I have a 2y, which stays out front. What is square root of 3z times square root of 3z? Okay. One way to think about this is that it is square root of 9z squared. But keep in mind, the whole point is I don't want any square roots in my denominator. But what do you know about the square root of 9z squared? We can take that square root, can't we? And the shortcut, I don't know if you guys like it or if you've grown to like it yet or not. The square root of 3z times the square root of 3z is going to end up being just 3z. When you multiply a square root by itself, it ends up being just that square root. So we still have x square root of 15z. And then we still have 2y. But the square root of 9z squared becomes, am I touching I must be touching the screen. There we go. Square root of 9z squared, square root of 9 is 3. Square root of z squared is z. Or again, the shortcut, square root of 3z times square root of 3z is just 3z. Okay. Last step. Multiply that denominator together.
6y.
Yes. 2y times 3z is 6yz. So I'm going to say, x times the square root of 15z is my numerator over 6yz as my denominator. There's a lot in that problem. We went from relatively easy up top to, whoosh, you got a lot to think about here. We'll keep working on these. Questions at this moment? Okay, let's look at B. First of all, notice that B is cube roots, yes? So B is cube roots. Cube root of 7x divided by cube root of 5y squared. Can I divide anything here?
No.
Of course not, because we're past that stage, right? We're past the easy ones, but I'm still checking. Because in homework, test, quiz, they won't necessarily be in that order, but 7 doesn't divide by 5, x doesn't divide by y squared, so we can't do that. We need to make this. Well, the problem is, okay, wait, time out, back up. I said, can we divide? No. Next question, are there any perfect cubes? Is there anything I can take the cube root of? 7? No, I can't take the cube root of 7, and the smallest cube root is 8, so 7 and 5, those aren't happening. Do I have 3 of any variable? No, I've got an x to the first, a y to the second. So, we're going to jump straight over to rationalizing. We're going to multiply this denominator by something that's going to give me a perfect cube. How many of something does it take to make a perfect cube? 3 of something. Okay. I have a 5. If I have 1 5, how many more does it take to make a perfect cube? 2 more of them, which means I could write this as 5 squared. You could also say that you're multiplying by 25. Okay, but keep in mind, whatever we do to the denominator, we have to do to the numerator. So that means we're also multiplying the numerator by the cube root of 5 squared. Now let's talk about the y. How many y's do I have?
1 or 2.
I have y squared, right, which is y times y, so that's 2 of them. How many does it take to make a perfect cube? 3 total, so I need 1 more. Does that idea make sense? So, if I have y squared, I can just multiply by y to the first. What I do in the denominator, I do in the numerator. That's how we're going to rationalize this one. I know it looks a little different, but I promise you it works. Okay, on top. Well, let's see what we got here. Cube root of 7x times the cube root of 5 squared y. You got a calculator by your side, right?
The cube root of 175.
Almost.
The x, y.
Yep. Okay, how do you get 175? There's a 7 here, 5 squared. 5 squared is 25. What is 7 25s? What's 7 quarters? And that is 175. And then there is an x and y. Which is why when Justin back there said just y, I said almost. Okay? Just don't overlook the x. Yeah. Alexis saw it, but yeah. You gotta make sure you grab the x. Now, denominator.
Be cube root of 125 y to the third.
Okay. Cube root times cube root, so multiply 5 times 5 squared. So 5 times 25 is 125. Y to the second times y to the first. Y to the third. On top, 175. I would ask you if there's any perfect cubes, but it came from multiplying 2 5s and a 7. So there's not 3 of anything in there. So my numerator is going to stay the cube root of 175x y. Denominator. What's the cube root of 125? 5. Calculators will verify that. What's the cube root of y to the third? 3 divided by 3 makes it y to the first, or in other words, y. Can I divide my numerator and denominator?
Yeah.
It looks like I can, but can I?
Oh no. Never mind.
It's not because there's no x. Why can I not?
The square of the radical.
The top is a cube root. The denominator is not. I got you guys. Sorry.
Gotcha.
Now, but the thing is, I'm asking you this now because I'd rather you make the mistake right now than get all frustrated and flustered in Math Excel, right?
Right.
So, speaking of which, Math Excel, you have an assignment. Lesson 6.2 in Math Excel. We will plan to talk about some questions tomorrow. Because if I'm not mistaken, there's some tricky ones in homework. Okay? So we'll plan to talk our way through some questions tomorrow and see what we need to get everyone up to speed. Because this is an important lesson moving forward. Okay, so make sure you take the time to look through the homework.